Everything in the universe is slowly losing its fight against gravity. Left unchecked, nature pushes all structure toward a single outcome: collapse into a black hole. But before reality gives in to that final state, matter makes one last stand. Astrophysics suggests this boundary has a name: the neutron star. For decades, we believed these objects were simple and inert, the quiet remnants of stellar death. That assumption no longer holds. A signal buried in decades of data now forces a revision of our models. It points to a process operating deep inside the neutron star core, a regime where our standard equations no longer fully apply. To understand what is really happening, we cannot observe from a distance. We must go inside. But before we descend, we need to understand what this object actually is. Even the name we give it is misleading. These objects are not stars at all, but the collapsed remnants of stellar core structures that no longer generate energy, only resist annihilation. They are quantum relics left behind when a massive sun exhausts its fuel and undergoes a catastrophic core collapse. Consider the scale of this compression. At neutron star densities, familiar scales collapse. Compressing the entire human population to this state would reduce it to a volume no larger than a teaspoon. This is not merely heavy, it is a state of existence where density reaches 10 to the power of 17 kilograms per cubic meter, pushing matter to the absolute brink of physical laws. These objects reside at a radius just slightly above the Schwarzschild limit, the mathematical threshold, where mass becomes so dense that it collapses into a black hole. A neutron star, therefore, is the universe's ultimate balancing act. It is a battlefield between two fundamental forces: gravity, the unstoppable crushing force trying to compress the object into nothingness, and quantum degeneracy pressure, a resistance force arising from the Pauli exclusion principle, which forbids particles from occupying the same space. For decades, we believed this equilibrium was the final word in stellar evolution. We viewed these remnants as stable, predictable laboratories for heavy element synthesis, the cosmic forges responsible for creating the gold in our electronics and the uranium in our reactors. If our understanding of this final fortress is flawed, then our understanding of the universe's chemical history is fundamentally broken. Theoretically, such structures should fade into thermal silence. Yet recent telemetry contradicts this expectation. We are detecting a persistent periodic signal, one that should not exist under standard models. Every physical model is built around assumptions, and every assumption eventually meets an exception. For neutron star physics, that blind spot has a name: GPM J1839-10. Under standard models, a pulsar converts rotational energy into radio emission. Faster spin means higher voltage. Slower spin means silence. As the neutron star spins, its immense magnetic field creates a voltage drop of trillions of volts across its polar caps. This voltage rips particles from the surface and accelerates them to relativistic speeds, creating beams of radio emission that sweep across the galaxy. The engine of this process is rotation. The faster the star spins, the higher the voltage and the brighter the beam. Conversely, as a star ages and slows down, it eventually crosses a calculated threshold known as the pulsar death line. Below this line, the rotation is too lethargic to generate the necessary voltage for pair production, the creation of electron-positron pairs. The mechanism fails. The lighthouse goes dark. The system transitions into a radio-quiet regime. According to the laws of electrodynamics, GPM J1839-10 should be dead. Discovered in archival data by the Murchison Wide Field Array and confirmed in a 2023 study published in Nature, this object rotates with a period of 22 minutes. In the realm of pulsars, where typical rotation periods are measured in milliseconds or seconds, 22 minutes is orders of magnitude slower than any rotation-driven pulsar model allows. It sits so far below the death line that its theoretical voltage output should be negligible. It should not be capable of producing radio waves, yet the telemetry is unambiguous. The readout shows a pulse arriving every 1/18 seconds, lasting for up to 5 minutes. More disturbingly, cross-referencing with the Very Large Array and the Giant Meter Wave Radio Telescope reveals that this signal has been arriving at Earth with metronomic stability since at least 1988. For 35 years, this structure has sustained a signal that standard physics cannot account for. It is a system outlier, a glitch in our understanding of stellar death. This is not a fleeting anomaly or a dying gasp. It is a stable, high-energy process occurring in an environment where no such energy source should exist. If rotation isn't powering this signal, what is? The existence of GPM J1839-10 forces a revision of the final fortress architecture. If the rotational kinetic energy is insufficient, the only remaining power source is the magnetic field itself. We classify this object as an ultra-long period magnetar. Unlike standard pulsars, which rely on a simple dipole magnetic field similar to a bar magnet with a north and south pole, this object likely possesses a far more chaotic internal structure. The hypothesis is that the magnetic field lines are not clean loops, but are twisted, sheared, and tangled, a configuration known as a multipolar field. In this scenario, even as the star's rotation slows to a crawl, the immense stress stored within these twisted magnetic lines can maintain localized electrical currents. These knots of magnetic energy act as localized particle accelerators, bypassing the need for global rotation speed. They sustain the radio emission by burning through the star's magnetic reserves. However, this hypothesis presents a new problem. Magnetars are notoriously unstable. Their magnetic fields usually decay rapidly on astronomical timescales, leading to short, violent lives. For GPM J1839-10 to maintain this signal for decades, and likely centuries, implies that its magnetic structure is anchored by something incredibly rigid. The field lines are likely pinned to the star's crust or dragged by the movements of its interior fluid. The radio signal is merely the exhaust fume of a much deeper engine. To understand how a dead star keeps its heart beating, we cannot simply listen to the static. We must trace the energy back to its source. We must cross the boundary from the vacuum of space into the extreme physical environment of the star itself. The telemetry confirms the signal is real. The question is no longer if it exists, but what structure is strong enough to sustain it. To find out, we must initiate the descent protocol and breach the star's magnetic firewall. The first barrier to entry is not physical matter. Before we can even touch the surface, we must breach a wall of pure energy. This is the magnetosphere. To describe this merely as a magnetic field is a failure of scale. In a standard laboratory on Earth, a strong magnetic field might reach 10 to 30 Tesla. The field surrounding a neutron star operates on a completely different scale, reaching up to 10 to the power of 12 Tesla in extreme cases, especially in magnetars. At this intensity, magnetism ceases to be a passive force and behaves like a physical structure, effectively functioning as a natural synchrotron, accelerating charged particles along curved magnetic field lines. The environment here acts as a natural particle accelerator. As the star rotates, the magnetic field lines whip through space, inducing an electric potential difference between the pole and the equator that can exceed 1 trillion volts. This voltage is so extreme that it breaks the dielectric strength of the vacuum itself. In this region, the concept of empty space is invalid. The electric fields are strong enough to rip electrons from the star's surface and accelerate them to relativistic velocities. But more critically, they trigger a phenomenon known as pair production. High-energy gamma-ray photons interacting with the intense magnetic field spontaneously convert their energy into matter splitting into electron-positron pairs. This creates a dense lethal plasma cloud, a pulsar wind that surrounds the star. Any probe attempting to descend through this region faces not just magnetic disorientation, but a bombardment of high-energy particles moving at nearly the speed of light. It is a firewall, in the most literal sense, a region where the vacuum is actively hostile to structural integrity. Having penetrated the magnetic firewall, the descent protocol now encounters the supreme governing force of the neutron star, the gravitational gradient. At a radius of about 12 kilometers, the star packs the mass of 500,000 Earths. The surface gravity here reaches roughly 2 times 10 to the power of 11 GR, about 200 billion times Earth's gravity. This creates an escape velocity of approximately 150,000 kilometers per second, half the speed of light. For any object caught in this well, the fall is terminal. An object dropped from just 1 meter above the surface would strike the ground in a microsecond, accelerating to a velocity of 100 kilometers per second. At these speeds, the kinetic energy of impact for a single marshmallow would rival the yield of a small nuclear weapon. But the danger is not just the impact. It is the tidal shearing. Because the gravity increases so sharply over such short distances, the gravitational pull on your feet would be exponentially stronger than the pull on your head. This differential force, the tidal gradient, overcomes the molecular bonds holding biological or mechanical structures together, overcoming molecular and atomic bonds, reducing any structure to a mechanically irrelevant state. However, the most disorienting effect of this gradient is not on matter but on information. As we approach the surface, the immense gravity warps the geometry of spacetime itself. Light rays emitted from the far side of the star are bent around the sphere, allowing an observer to see more than 50% of the surface at once. We can essentially see the front and the back of the star simultaneously. More critically for our mission, we encounter gravitational redshift. According to general relativity, time flows slower deep inside a gravity well. At the surface of a typical neutron star, the redshift factor ZR is approximately 0.3. This means that for every 10 seconds that pass on the star, 13 seconds pass for the observer at infinity. This creates a telemetry latency. Signals sent from the surface are stretched. Their frequency drops, shifting toward the red end of the spectrum, and the data packets arrive with a time lag that cannot be fixed by simply moving closer. We are entering a zone where time itself is desynchronized from the rest of the universe. The fields have delayed the collapse, and the time dilation has warped our perception. But fields and relativity are intangible. The real question is whether matter itself can survive what comes next. We have cleared the energy barriers. Now we hit the physical limit, the hardest surface in the universe. As density climbs beyond 10 to the power of 6 grams per cubic centimeter and continues to rise rapidly, the familiar concept of an atom begins to lose its meaning. We have touched down on the outer crust. Unlike the gaseous surfaces of normal stars, the surface of a neutron star is solid, a rigid crystalline shell. Here, the immense gravity has stripped all atoms of their electron shells. What remains is a dense lattice of iron nuclei locked in place by mutual electrostatic repulsion, submerged in a sea of degenerate electrons that flow through the crystal like a quantum fluid. This structure, known as a Coulomb lattice, creating a solid surface with mechanical strength orders of magnitude beyond any material engineered on Earth. But as we drill deeper, passing a density threshold of 4 times 10 to the power of 11 grams per cubic centimeter, the lattice undergoes a radical transformation. We enter the neutron drip regime. The pressure here becomes so overwhelming that it forces the free-roaming electrons to merge back into the protons within iron nuclei, a process known as inverse beta decay. The nuclei become increasingly neutron-rich, bloated with excess particles, until they can no longer hold them. Neutrons begin to drip out of the nuclei, filling the spaces between the lattice. The material is no longer just a crystal, it is a crystal suspended in a superfluid bath of free neutrons. We are leaving the realm of atomic physics and entering the domain of nuclear matter. Descending further into the mantle, the density climbs toward 10 to the power of 14 grams per cubic centimeter, the density of an atomic nucleus itself. Here, the spherical nuclei of the lattice become unstable. To survive the crushing squeeze and the intense competition between the attractive strong nuclear force and the repulsive electrostatic force, the matter undergoes a geometric phase transition. Scientists refer to this regime colloquially as nuclear pasta, but the terminology belies the terrifying strength of the material. The nuclei begin to distort, stretching into long cylinders known as the spaghetti phase, then flattening into parallel sheets known as the lasagna phase. This is not biological matter, it is the densest and strongest material in the universe. Simulations show a shear modulus of roughly 10 to the power of 30 ergs per cubic centimeter. To put this into a mission context, this material is roughly 10 to the power of 18 times stronger than steel. To break a single cubic centimeter of this pasta would require energy far exceeding the elastic limits of any known planetary material. It functions as a mechanically rigid shell, separating the magnetosphere from the core. But in a system this energetic, even the strongest armor has a breaking point. The crust is not isolated. It is tethered to the chaotic magnetic field we traversed earlier. As the star spins and its internal fluid churns, the magnetic field lines, which are physically anchored to this crystalline crust, begin to twist and tangle. This applies immense shear stress to the lattice. For years, the crust resists, holding the magnetic energy like a wound spring. But eventually, the stress exceeds the lattice's elastic limit. The result is a starquake. This is a structural failure of cosmic proportions. The crust snaps, shifting perhaps only a few centimeters, but in a material this dense that shift releases a cataclysmic amount of energy. The sudden reconfiguration of the magnetic field triggers a magnetar giant flare, blasting out a wavefront of gamma radiation that's capable of depositing biologically significant radiation doses across interstellar distances. This violent rupture proves that the star is still mechanically active. The crust, for all its strength, is brittle. It obeys the laws of solid mechanics. But as we pass the mantle and approach the true center, we leave the solid state behind entirely. We are approaching a regime where classical friction no longer applies, possesses no viscosity, and challenges the very definition of matter. We have breached the crust and navigated the chaos of the mantle. Now, beneath the inner crust, we cross the final threshold into the outer core. Here, density surpasses that of an atomic nucleus itself, reaching about 2.8 times 10 to the power of 14 grams per cubic centimeter. At this point, the assumptions of classical hydrodynamics no longer apply. Welcome to the world of macroscopic quantum mechanics. In this regime, the chaotic soup of neutrons and protons undergoes a radical ordering. The protons paired by nuclear interactions are believed to form a type II superconductor, allowing magnetic flux to penetrate in quantized tubes, the mechanism likely responsible for maintaining the star's billion-year magnetic lifespan. But the behavior of the neutrons is even more alien. They transition into a superfluid. Imagine a fluid with zero viscosity. It possesses no internal friction. If you were to stir a cup of superfluid, it would continue to rotate forever, never losing energy to heat. Inside the neutron star, this creates a strange duality. The solid crust rotates at one speed, while the superfluid core rotates independently, often faster, slipping frictionlessly beneath the shell. This is not mere theory. We've observed the consequences of their interaction. Astronomers frequently observe pulsars suddenly and violently speeding up their rotation, an event called a glitch. The leading explanation relies on a mechanism called vortex pinning. As the superfluid rotates, it forms quantized vortices, tiny tornadoes of angular momentum. These vortices can get snagged or pinned to the atomic lattice of the crust above. As the crust slows down due to magnetic braking, the superfluid core continues to spin rapidly, storing immense angular momentum. When the stress becomes too great, the vortices unpin en masse, rapidly transferring that stored angular momentum to the crust and jerking the star into a higher rotational speed. This interaction is our only window into the equation of state, the source code of the star. The EOS describes how pressure relates to density at these extreme limits. It dictates how stiff or soft the core is. If the EOS is stiff, the star can support more mass without collapsing. If it is soft, gravity wins sooner. But as we push toward the center, even neutrons may not be the fundamental limit. At the very center, the inner core pressures climb so high that individual neutrons may be crushed out of existence. We are approaching the theoretical floor of matter. Current models suggest that under this crushing weight, neutrons undergo deconfinement. They dissolve into their constituent parts up and down quarks. This may create a deconfined quark phase analogous, but not identical to the quark-gluon plasma of the early universe. But there is a more unsettling possibility lurking in the math. At these densities, the energy required to maintain up and down quarks becomes so high that nature might opt for a more efficient configuration. Some of the quarks may spontaneously convert into a heavier, more stable flavor, strange quarks. This gives rise to the strange matter hypothesis, often referred to as the Bodmer-Witten assumption. This theory posits that matter containing strange quarks is actually more stable than normal nuclear matter. It suggests that strange matter is the true ground state of the universe, the absolute bottom of the energy valley that all matter wants to reach. If this is true, the core of a neutron star is not just a soup of particles. It is a strange star wrapped in a neutron shell. This poses a significant operational risk in our mission analysis phase transition contagion. If a microscopic droplet of strange matter, a strangelet, were to escape the high-pressure confinement of the core and touch normal matter, it could theoretically trigger a chain reaction, converting the external matter into strange matter to reach that lower energy state. This is similar to the concept of false vacuum decay. The neutron star in this view is a containment vessel for a state of matter that is too stable for the rest of the universe to handle. However, whether the core is neutron or strange, it faces an absolute limit. Gravity is relentless. There is a specific mass threshold known as the Tolman Oppenheimer Volkoff limit, calculated to be around 2.2 to 2.5 solar masses. This is the hard ceiling of existence. If a neutron star accretes enough mass to cross this line, the equation of state breaks down. The degeneracy pressure of neutrons' quarks or strange matter is simply overwhelmed. The source code crashes. There is no force left in the known universe to halt the collapse. The object vanishes from the visible universe, leaving behind only the event horizon of a black hole. The neutron star is the final fortress. Beyond it, no known form of matter remains, only the geometry of space-time itself. The universe does not negotiate with the Tolman-Oppenheimer-Volkoff limit. It is an absolute boundary. When the descent protocol concludes, we are left with one final scenario: system failure. This usually occurs when two neutron stars spiraling inward due to the emission of gravitational waves finally collide. We witnessed this directly on August 17th of 2017 during the event known as GW1-7. In the final milliseconds of the merger, the combined mass of the two objects breached the TOV limit. The degeneracy pressure that had held the stars up for billions of years finally capitulated. The system collapsed on astrophysically short timescales into a black hole, disappearing from electromagnetic observation. But in that brief moment of destruction, the system ejected a small percentage of its mass. This material, suddenly decompressed from the crushing density of the core, underwent rapid expansion. Free from the gravitational vice, the neutron-rich matter engaged in the rapid neutron capture process known as the R process. In seconds, this cosmic debris synthesized the heaviest elements in the periodic table. Gold, platinum, and uranium are not born in normal stars. They are the physical remnants of this structural collapse. The gold in our circuit boards and the uranium in our weapons are direct evidence of a neutron star reaching its breaking point. This brings us back to our primary mission objective. What is the structural limit that prevents matter from collapsing into nothingness? Within the framework of known physics, the answer is the neutron star. It is the final fortress. It represents the maximum density that nature allows before the concept of matter becomes obsolete. It is the last checkpoint where particles, protons, neutrons, quarks still retain their identity. Beyond this line, the equation of state fails. Structure dissolves. Matter ceases to be a physical substance and becomes a property of space-time geometry, a singularity. GPM J1839-10 and other anomalies remind us that we have not yet fully decoded the source code of this fortress. There are still layers to drill through. But one thing is certain. When we study neutron stars, we are not just looking at dead suns. We are looking at the absolute edge of reality, staring at the thin, rigid line where our understanding of existence gives way to the unknown.